So, what the hell is a quantum computer? How's it built? How does it work? What can it actually do? And why is everyone freaking out about it these days? If you've been itching for answers, this video's your antidote. I'm going to break down the core principles of quantum computing, covering what sets a quantum computer miles apart from your regular classical machine and what insane new tricks it packs thanks to those differences. Basically, you'll be joining me for a crash course in the big, mind-boggling discipline called quantum computing. Quick side note, if you're enjoying the chaos on this channel, it'd be awesome if you become a sponsor right here on YouTube. More supporters means I can push out more videos, better quality. You know the drill.
You're goddamn right.
Now, let's skip the warm-up. Let's talk about how a quantum computer really differs from a standard one, or more precisely, a classical one. A computer is ultimately a data machine. In a normal, classical setup, we store data in bits, those little physical devices that can be just one of two states, 0 or 1. Could be a transistor that's open or closed, a capacitor that's charged or uncharged, or a chunk of ferromagnetic material magnetized one way or the other. And a classical computer is all about taking one bunch of bits and transforming them via algorithms into a different bunch of bits. Maybe you're adding or subtracting two binary numbers. Again, that's bits. You feed in the numbers, run the algorithm, spit out a new set of bits that represent the sum or difference. Cool. A quantum computer basically does the same but with quantum bits, quantum operations, quantum algorithms. A quantum bit is a qubit, an object that can be in two states, 0 or 1. Could be an atom that's either in its ground or excited state, or a spin 1/2 particle whose spin projection is either plus 1/2 or minus 1/2, with 0 in-betweens. But unlike a classical bit, a qubit obeys quantum rules, not classical. And that's where stuff gets weird. Classical physics is deterministic as hell. Put 5 identical transistors in the same setup with identical voltages and they'll all do the same thing, guaranteed. Gate open equals 1, gate closed equals 0. No messing around. Quantum physics, though, completely different ballgame. Probabilistic. If our transistor lived according to the laws of quantum physics, then taking 5 identical transistors and applying 5 identical voltages to their gates, we might be surprised to see that our transistors conduct current in 3 of the 5 cases and do not conduct it in the remaining 2. If you take 5 different qubits and do the same operation on each of them, you will get a different answer each time. Maybe 3 times you'll get a 1 and the other 2 times you'll get a 0. Bottom line, we can't predict in advance what the result of measuring the state of a qubit will be. At best, we can only know the probability with which we will get this or that result during the measurement. This probability is determined by some mathematical function describing the state of the qubit. Usually this function is denoted by the letter phi or psi, and a qubit in the state of psi is denoted by such brackets known as ket. This notation comes from quantum mechanics, where it is part of a notation system known as Dirac notation. That's not important to us right now. For the purposes of this video, ket is just a way for us to show that we're dealing with a qubit in the psi state. Once again, the maximum we can expect when dealing with a qubit is to know what the psi function is. That is, to know what probability we have of getting 0 or 1 when we measure the state of the qubit. No guaranteed classical reliability, and the idea of building some kind of logic on such uncertain systems may not seem very good at first glance. After all classical computer science is based on the fact that there is an unambiguous cause and effect relationship between an action and its result. However, it turns out that it is possible to build a computer using qubits if we know a way to bring qubits into states in which they will behave like ordinary bits, that is, always give 0 in one of such states and always give 1 in the other. Such states of a qubit are called its pure states. To do this, we need a measurement symbol, some little meter icon to signify that we are actively defining the state of the qubit. Accordingly, we will denote the pure state that always gives us 0 when measured by 0 in ket brackets, and the pure state that always gives us 1 by 1, respectively. Once again, if we write the unit in cat brackets, we mean the quantum state of the qubit, and if we write the unit without brackets, we mean the result of measurement, simply the number which we will see after measurement on the screen of the measuring device. And since the qubit can take a pure state, it is appropriate to write down all its other states in this form, in the form which in quantum mechanics is called superposition of pure states. The alpha and beta coefficients are called amplitudes, and their physical meaning is that the square of the amplitude will give us the probability, when measured, of finding a qubit in state 0 or 1. For example, for our case in which the qubit gave 0 with a probability of 2/5 and 1 with a probability of 3/5, alpha would be equal to the root of 2/5 and beta to the root of 3/5. However, the amplitudes can take other values. In other words, a quantum computer should be able to do all the same stuff a classical computer can do, but the fact that a qubit can also be in a mixed state unlocks extra superpowers that classical bits can only dream of. And here's the critical point you've got to pound into your head. Yes, qubits can chill out in these mixed states, but if you go and poke at them, that is, measure them, they'll always come back as 0 or 1. No third option exists. And it means that having received, for example, 1 when measuring a qubit, we cannot say whether it was in a pure state of 1 before the measurement, in which its measurement would give us a 1 in 100% of cases, or in a mixed state, in which a 1 would be registered only with some probability, even a very small one. But we were lucky to get into this small probability. And most importantly, after the measurement that gave us 1, the qubit and itself will go to state 1, saying that its state collapses to a pure state. And all the complex quantum mechanical superposition magic contained in the qubit before the measurement will be lost after the measurement. Classical computers do their job with bits by feeding them into logic circuits, gates, that push those bits around according to some operation. You feed in certain bits, the circuit does its thing, and out come new bits at the other end. Easiest case, the NOT gate. If the incoming bit is 0, it writes a 1 at the output, and if it's a 1, you get a 0 out. There are analogs of logic circuits in quantum computer, but they work differently. Both initial and final values are stored in one and the same qubit, on which the logic circuit affects in one way or another, changing its state. That is, if classical gates really resemble a gate, in which some data enter and others leave, quantum logic circuits are more like a kind of machine, which affects the qubits in the initial state, turning them into qubits in the final state. And though quantum logical operations by analogy with classical programming are usually called quantum gates, I personally think these term is not very successful. Better, the essence of what is happening is conveyed by the term operator, which also came from quantum mechanics, and in it from linear algebra. Representation of schemes of quantum operations is also similar to the way we do it in classical programming. Incoming data is on the left, logic scheme is in the center, and result is on the right. But if in classical programming the elements of this scheme are indeed spatially separated devices, in the case of a quantum computer, the elements of the scheme are separated rather in time. The qubit in the initial state, the qubit while it is being processed by operators, and the qubit at the end of the operation. One of the consequences of such architecture of quantum computers is that in quantum logic circuits, the number of inputs is always equal to the number of outputs, simply because they are not inputs and outputs, but simply the same qubits, just before and after. In fact, this phenomenon has other, more fundamental reasons, the roots of which lie in the quantum mechanical nature of qubits, but we will not go that deep. So, we have already mentioned that, dealing with one single bit, we can apply to it the inversion operation, also known as the negation operation, or simply the NOT operation, and this is, in fact, almost everything we can do with one bit. Well, except for the identity operation, which basically means that we did not do anything with the bit at all and overwrote the incoming data into the outgoing bit without changing it. Well, of course, that's not much of an operation. With a quantum bit or qubit, we can pull off both of these operations too. For example, the inversion operation will be reduced to a permutation of the mixed state amplitudes. Indeed, in state 0 alpha is equal to 1, and this beta is equal to 0. Let's swap them and get state 1. Well, or vice versa. However, it is not difficult to realize that even with one single qubit, as opposed to a single bit, you can do many other things. In fact, by and large, any change in alpha and beta amplitudes will result in a change in the state of the qubit, and thus can be considered an operation. But we can perform as many such operations as we want, because we can change alpha and beta in any way we want, as long as the sum of their squares remains equal to 1. How exactly can we do this? Specific ways depend on which physical object we use as a qubit, so we will answer this question in detail when we will speak about constructions of quantum computers. Now let us concentrate on what we can do with qubits and what it gives us. For example, we can do such a cool thing with a qubit, change the sign of one of the amplitudes, say beta. This action has no analogs in classical programming, and moreover, it will not affect the state of the qubit that we observe, that is, the probability of getting this or that result during measurement. Indeed, we have said that probabilities are determined by the squares of amplitudes, and having squared that plus beta, that minus beta, we will still get the same result, beta squared, and hence the same probability. Nevertheless, at quantum level, the state of the qubit at carrying out such operation with it will be different. At influence with the help of this operation on qubits in pure states, we, as it is not difficult to understand, will see this. A qubit in the state 0 will remain unchanged as a result, and a qubit in the state 1 will change its sign to the opposite one. This will not affect it in any way externally. It will still give us a 1 in every measurement. But from the quantum point of view, it will still be a different state. This strange quantum operation is called phase shift, or Pauli Z-gate, and it really turned out to be very useful for realization of some quantum algorithms. But even more useful and common in quantum programming is another quantum gate called Hadamard operator. What it does is this. Being applied to the pure state 0, it transforms the qubit into this state, and when applied to a pure state of 1, it does this. What can we say about the qubits in these states? It is easy to see that in both cases we have obtained qubits. When measuring them, we will get 0 or 1 with a probability of 50%. That is, no matter what pure state the qubit was in initially, the Hadamard operator puts it into a state that when measured will give us 1 and 0 with equal probability. One could say that the Hadamard operator erases the information written into the qubits, but this is not quite true. As we can see, the results of its action on 0 and 1 will be different at the quantum level, and the erased information can be restored just because the amplitudes with plus and with minus at the quantum level form different states. It turns out that it is enough for us to act on the erased qubits by the Hadamard operator again, and we will return it to the initial state again. So the Hadamard operator does not erase, but as if hides the state of the qubit, due to what it is an integral part of the algorithm in quantum information transfer and quantum encryption. However, also in usual quantum programming, Hadamard operator, as we will see a little further on, has got very widespread. There are many more quantum operators with which we can influence qubits in one way or another. However, explaining the essence of what they do to qubits can only be done using the matrix language of linear algebra, with which not all of my esteemed viewers may be adequately familiar, so we will not dwell on this question. Moreover, quantum computers, just like their classical counterparts, reveal their true power only when working with several qubits, and it is multi-qubit systems that we are going to consider now. First of all, let's agree how we will denote what we are talking about. We have agreed to write the state of one qubit in Keat brackets like this. We will write the state of two qubits in the same brackets, but inside them there will be two symbols corresponding to the pure state of each of the qubits. That is, the record 1, 0 will correspond to the state when the first qubit will be in the pure state 1 and the second in the pure state 0. Measuring such a two-qubit system, or rather each of its bits separately, will always give us one no, or binary 2. It is not difficult to understand that we will write the state of three qubits like this. 4 qubits like this, and so on. Mixed states of several qubits, as in the case of the state of 1 qubit, we will represent them like this. That is, with some probability we will find our qubits in the 0,0 state, with some probability in the 0,1 state, with some probability in the 1,0 state, and in general in all possible pure states that our multi-qubit system can have. Well now, when we have agreed about notations, we can proceed to consideration of multi-qubit quantum operators, the main of which for us will be 2-qubit operator, known as controlled knot or C-knot. Its essence is that it acts on one of the qubits, which we call the target, depending on the state of the other one, which we will call the controlling one. In case the controlling qubit is in state 0, C0 leaves the target qubit unchanged. In case the controlling qubit is in state 1, C0 inverts the target qubit. The controlling qubit remains unchanged in both cases. Using our notation system, we can make a logic table of the C0 operator. By acting on the 2-qubit 00 state system, it will also give us 00. 01 will change to 01 without change, and 10 will give us 11 because the state of the target qubit is reversed, and 11 will turn into 10 for the same reason. In principle, there are analogs of C0 scheme in classical programming as well. For example, if we take a classical logic scheme excluding or XOR, and add to its result also the value of the first of 2 bits, then we will get almost the same thing. And now, comparing these two almost identical operations with each other, we can see how quantum computers in certain situations can be dramatically better than classical ones. Let's start with a classical case and imagine that we don't know what kind of logical scheme we enter data into, but we really want to find out. According to the terms of the task, we can do it only by feeding some data to the computer and studying what we will get after processing. Such tasks in programming are called black box tasks. Let's ask ourselves how many times we need to activate our computer to learn the answer. It is not difficult to understand, at least 4. Indeed, let our input be 0 and 0. When we get 0 and 0 as a result, we can easily decide that our computer is just an empty box that does nothing with data, and sending a 0 and a 1 will only further convince us that this hypothesis is correct. But we want to get the answer for sure, and to do that we send the numbers 1 and 0 into the black box. But even if we get 1 and 1 as an answer, we cannot in principle know exactly what is in the black box. For example, it is quite possible to assume that the circuit standing there, in case the controlling bit is C not equal to 1, assigns the value 1 to the target bit, regardless of what value was originally written there. It is only by sending 2 1s to the black box that we will have enough information to say that there is an exclude OR circuit inside. Now let's ask the same question about the number of operations with respect to the same black box, but only installed inside a quantum computer. It might seem that the answer would be the same, but it really isn't. For here's what we can do. Before placing our qubits, even if both of them are first in pure state 0 into the black box, we affect the controlling qubit with an Hadamard operator. As we already know, the result is that our controlling qubit will become a balanced superposition of states 0 and 1. That is, it will be equally a quantum 0 and a quantum 1. Our black box C0 operator is supposed to leave the target qubit unchanged if the controlling qubit is in state 0, and invert it if the controlling qubit is in state 1. But what if the controlling qubit is both 0 and 1 at the same time? Correct. The C0 operator will both invert the target qubit and leave it the same. More precisely, the result of the C0 operator's action on the target qubit will lead already to the mixed state of the inverted and non-inverted qubit, that is, to the equally probable superposition of 0 and 1 states. Well, if we consider our 2-qubit system as a whole, it will also appear in the mixed state, which can be written in this way. What if we apply the Hadamard operator to the target qubit as well? In this case, the C0 operator will not only perform 2 actions simultaneously, but also apply this action to the 2 components of the mixed state of the target qubit simultaneously. As a result, our 2-qubit system, once processed by the operator, will be an equal probability superposition of 4 states: 0, 0 for the case when C0 was guided by the 0 part of the control qubit and acted on the 0 part of the target qubit, 0, 1 for the same situation but when it acted on the unit part of the target qubit, 1, 1 for the case when C0 was guided by the unit part of the control qubit and acted on the 0 part of the target qubit, and 1, 0 for the case when it acted on the target qubit. It is not difficult to realize that the probabilities of all 4 states will be equal. That is, the mixed state of the 2-qubit system will be like this. But let's take a closer look at this state. In fact, this state contains information about all outcomes of all possible variants of the initial state of the qubit. That is, in fact, we have extracted from our black box all the information about what is going on inside it in just one query, instead of 4, as it was in the classical case. However, for this purpose, it is necessary that our black box should be able to work with quantum bits. That is, it should live according to quantum mechanical laws. Such quantum black box is also called quantum oracle. The ability of quantum computers to perform simultaneous calculations for different possible states of incoming data written in one mixed state is the main source of power of quantum computers and makes this technology so promising. But let us not rejoice prematurely. Even though we have extracted from the black box all the information we need at once and crammed it into a pair of qubits, but reading that info is a nightmare. The moment we measure our qubits, we end up with only one of 4 possible outcomes and everything else goes poof in the wave function collapse. We're back to square one result per query, which is no better than the old school classical approach. Actually, it's worse, because the next time we ask the oracle, it might just spit out the exact same result, giving us nothing new. Sure, our quantum computer has done this grand jaw-dropping trick of churning out piles of data, but that data is stuck in some quantum limbo where we can't yank it out. Luckily, there are certain tasks where we can pry out useful info from the quantum realm, if we're willing to sweat for it. One such example is the so-called needle in a haystack problem. It is formulated as follows. Suppose we have some function which has value 1 in all points except one point x0, where its value will be equal to 0. We don't know the type of this function, and we have no clue where x0 is, but we do know it lives somewhere in the interval from 0 to 2 to a power of n. This kind of interval length is standard in programming, where numbers get expressed as powers of 2. Our mission is to figure out x0. It sounds abstract, but trust me, it's everywhere in real life. Any find the root problem fits this pattern, and with a twist, so do minimization problems, plus any optimization scenario, whether it's production, logistics, you name it. And if you still can't see why this is handy, picture hunting for a secret password. Every wrong guess is 1, and the correct one is 0. Now, let's throw quantum computing into the mix. We load this function into a quantum oracle with n qubits as input, and the result lands on another n plus 1 qubit. There are 2 to a power of n possible values for those n qubits, meaning we can fire any number from 0 to 2 to a power of n into our oracle and see if the function returns 0 or 1. We could be old school and just hammer random inputs into the oracle until maybe we stumble onto 0 right away, or maybe we get it on the 2nd or 10th try. Or if our luck absolutely sucks, we might plow through all 2 to a power of n possibilities. On average, we will get the answer after 2 to the power of n in half or 2 to the power of n minus 1 try. That's not awful if the numbers are small. But if, for example, we are trying to find an 8-digit password consisting of letters, numbers, and special characters, then in such a task, n will be equal to 56, and 2 to the power of n minus 1 is about 3 to the power of 10 to the 16th degree. This means that a computer capable of performing about 10 to the 10th degree of operations per second would take about 10 to the 6th degree of seconds, or something like 11 days to complete the selection. The bigger n gets, the more brutal the exponential spike. At n equals 60, it's about 10 to the 18th power of operations, which clocks in at 10 to the 8th power of seconds, or 3 years. If n equals 70, you're looking at 300 years. And once you hit 128-bit passwords, truly strong by today's standards, that means 10 to the 38th power of operations, requiring around 100 trillion years for even the mightiest supercomputers alive right now. So let's talk about quantum computers. The big deal here is that a quantum computer can dig up the solution in one swift shot if we let the Hadamard operators act on every qubit before shoving them into the quantum oracle. As a result, each digit of our binary number that we input into the supercomputer will be in an equal superposition of 0 and 1, which means that our multicube state will be a superposition of all numbers from 0 to 2 to a power of n-1. As a result, the target qubit will contain a superposition of two n-degree n-1 components with value 1 and 1 single component, with value 0. And if we consider the total n plus 1 qubit state, it will look like this. Each component of such a state will be a number expressed in qubit states, plus another bit will store information about the value of the function in that case. Among other things, the n plus 1 qubit state will also store the case in which the function will produce a 0, along with the input value at which that 0 was fixed. That is, the x0 we need to find. All that's left is to make the measurement give us that one winning result, instead of drowning us in possibilities. That is, to make the qubits show us exactly these values when measuring. The way to do this is a quantum algorithm known as the Grover's algorithm. To understand how it works, let's represent our multi-qubit state as a histogram, where on the x-axis we put the values of our qubits, and on the y-axis the values of their amplitude in superposition, the square of which, let me remind you, gives us the probability that we will get exactly this value when measuring. At the initial moment of time, the amplitudes of all states are equal, because we have placed in our quantum oracle an equal superposition of all possible numbers. That is, we have 2 to the power of n equal amplitudes, the sum of squares of which gives us 1. That is, the magnitude of each amplitude is 2 to the power of 2 minus n in half. So, we need to somehow isolate the state of interest in which the target qubit is in state 0 from the sea of other states in which the target qubit is in state 1. That is, we need to find some operation that will change the amplitudes of the qubits in different states differently. And this is exactly the kind of operation that we talked about at the beginning of our video. It's a poly-Z operator that leaves the qubits in state 0 unchanged and reverses the sign of the qubits in state 1. By slapping this onto our target qubit, we flip the sign of the amplitude for every single component in the superposition except the one that solves our problem. Boom! Now we've singled out the state we want. At the second step of the Grover's algorithm, we calculate the average value of all amplitudes in our superposition. How exactly we do this I will not explain here, so as not to plunge into the maze of linear algebra. I will only say that as a result we get a number almost equal to -2 to the power of -n in half. That is, approximately the value of all our amplitude's non-zero members of our superposition. Then we multiply this average by -2, that is, make it equal to something very little different from 2, multiply it by 2 to the power of half, and then add this number to the amplitudes of all components of our superposition. For all components except 0, we get something like 2 to the power of -n by half. So essentially we're just flipping the amplitudes back up, slightly reducing each of them, but something different will happen to the amplitude of the component containing our solution. 2 times 2 to the power of -n by half plus 2 to the power of -n by half will give us 3 times 2 to the power of half. In other words, this operation will result in a slight decrease in the amplitude of the singular states. The probability of measuring one of the other states drops a bit, while the amplitude for the 0 state we actually want nearly triples. That's a huge boost in our odds of nailing the right result, but it's still not enough, because at large, n9 times 2 to the degree of -half is still a very small number, and by measuring it now we are likely to get the wrong result. However, we can repeat the same steps, achieving another almost threefold increase in amplitude and an almost ninefold increase in probability, while reducing the probability of getting the wrong result. Still not enough? Run the algorithm again and again and again until the probability of getting the state we are looking for in the measurement does not differ from 1. We can even calculate that in order to bring our qubits to such a state, we will need something about the root of 2 to the power of n operations. After that, we measure our multi-qubit monstrosity and boom, there's our x0, practically guaranteed. In other words, the Grover's algorithm will do for the root of 2 to the power of n operations what a classical computer would do for 2 to the power of n minus 1 operation. If n equals 50, that means about 3 times 10 to the 9th power of operations on a quantum computer versus 10 to the 15th power on a classical box. A million-fold speed up. For bigger n, the difference just gets crazier. And hunting for a needle in a cosmic haystack isn't the only party trick in quantum computing. The most famous task in this sense is the problem of factorization of numbers. That is, the division of these numbers into multipliers, which are simple numbers. The problem seems somewhat abstract, but only for those who are not aware that by learning to factorize large numbers quickly, we can easily break almost all encryption algorithms that exist on the internet today. Classical factorization of a 256-bit number chews up around 10 to the 12th power to 10 to the 13th power of operations and still passes for secure. But a quantum computer can reduce that to a mere 10,000s operations using Shor's algorithm, which is 100 million times faster. Translation: once quantum systems go mainstream, just about every data protection method we rely on becomes hopelessly obsolete. That's some scary news for anyone who's not ready to live in a world without privacy or confidentiality. The good news is that as quantum computers and quantum communication systems evolve, we'll get our hands on quantum-grade encryption that not even quantum machines can break. In other words, the hotshot with the world's most powerful quantum rig can smash everyone else's security, but his own remains untouchable. And that's just the tip of the quantum iceberg. Sure, quantum computers can slice through encryption and shred passwords, but they can also bulldoze a ton of other mathematical problems. Take the classic traveling salesman problem, where you have to connect endpoints on a map in the shortest loop possible. That's pure gold for optimizing transport networks, but a nightmare for large N on an ordinary computer. Even something as small as 20 cities already means your classical hardware would have to brute force 10 to the 18th power of possible routes. A quantum algorithm, based on our old friend Grover, can solve it in a measly 10 to the 8th power of operations, which is 10 billion times faster. That's not all. Quantum supremacy could also blow classical computing out of the water in messy tasks like solving complex linear equations, multiplying huge matrices, clustering data, or optimizing half the things you do. Sounds amazing, right? Too bad we're not anywhere near bringing all these quantum dreams to life. We sort of know how to make qubits and string them together into a computer, but the specs are painfully underwhelming. Want to tackle that 20-city traveling salesman fiasco? You need at least 400 qubits, at least, because qubits are ridiculously finicky. They're hypersensitive to outside interference and prone to stacking up errors from the noise in the system. That means any real quantum computer needs to run non-stop error correction routines alongside its main work. The math says that for every qubit you're actually using to solve the problem, you'll need a bunch more just to keep the thing on track. So a real problem-solving quantum computer needs thousands or maybe even hundreds of thousands of qubits. Today's quantum machines, they're lucky if they have a few dozen. Some hang on to single digits. The biggest quantum rig right now is from Atom Computing at 1180 qubits, but it's not even fully functional. Second place is IBM's Condor with 1121 qubits, also not really up and running. The most powerful working quantum computer is the IBM Quantum System 2, sporting 3 cores of 133 qubits each. On top of that, we've got another massive headache, Building quantum oracles for many quantum algorithms is a thorny task. Remember how Grover's algorithm just assumes we have one? Actually, making that oracle is far from trivial in real life. Bottom line, quantum computers still aren't ready for prime time. Today's quantum whizzes mostly focus on contrived math problems, useless in real life, that these small, imperfect, puny quantum machines can still beat classical hardware at, if only to show off. Don't expect quantum computers to overthrow your everyday classical PC anytime soon, or maybe ever. Our trusty classical computers pack billions or even trillions of bits, and we'll keep using them for the usual chores. Every once in a while, when the job demands it, we'll punt some monster calculation to a quantum processor, then feed those results back into our normal digital workflow. And that, dear friends, is enough quantum talk for one day. Until next time, take care, and I'll see you soon.